of a Boeing 737 inside its outer shell, with room to spare. We are talking about a machine that breathes in tons of air every single second, squeezes it with 60 times the pressure of our atmosphere, and burns it at temperatures that would effortlessly melt ordinary steel. This is the GE9X. It is undisputed heavyweight champion of the skies, built specifically for the Boeing 777X. But the story of this engine isn't just about making things bigger. It's about a crazy paradox where the world's most powerful engine actually uses less brute force in its daily life than its predecessor. It's about custom-engineered pixie dust, 3D printing metal, and pushing the literal laws of thermodynamics on the absolute edge. Before we tear into the guts of this absolute monster, if you enjoy deep dives into the bleeding edge of aviation technology, do me a huge favor. Hit that like button and make sure you are subscribed. It takes just a second, but it really helps push these discussions out to more people. So let's talk about the sheer scale of this thing, because numbers on a screen really don't do it justice. The front fan alone measures 134 inches across. That is almost 11.5 feet of just fan blades. Once you wrap the nacelle, that's the outer housing, around it, the total width comes out to 184 inches. Like I said, a standard Boeing 737 fuselage is only about 148 inches wide. You could slide a 737 right through the engine pod of a GE9X. But here is where it hits out first really fascinating paradox. Because it's so huge, everyone naturally assumes it just blasts out more thrust than anything else in the sky. All day, every day. And technically, yes, it holds the Guinness World Record. Back in November 2017, on a test stand in Peebles, Ohio, GE engineers pushed this thing to a staggering 134,300 pounds of force. To put that in perspective, the fighter jets you see breaking the sound barrier usually max out around 30,000 to 40,000 pounds of thrust. The GE9X crushed the previous world record, which was held by its older brother, the G90. But if you look at the actual certification documents for daily commercial flying, the G9X is only certified to operate at 110,000 pounds of thrust. The older G90 actually operates at over 115,000. Why? Why build the biggest, most powerful engine in human history, only to throttle it back for everyday use? The answer is efficiency. The Boeing 777X is a highly aerodynamic aircraft with a massive glider-like wingspan. It doesn't actually need to muscle its way through the air with brute force like older jets. By building a larger fan but running it at a slightly lower thrust rating, GE dramatically increased the bypass ratio. Let's break down what that means. Because bypass ratio is the secret sauce of modern jet engines. The G9X has a bypass ratio of 10 to 1. That means for every 1 unit of air that goes into the fiery core of the engine to be compressed and ignite, 10 units of air bypass the core entirely. They are just pushed around the outside of that giant 134-inch fan. That bypass air provides the vast majority of the thrust. And because there is so much bypass air, it creates this massive, relatively cool stream of air that wraps around the superheated, supersonic exhaust shooting out of the core. That shield of air actually acts as a muffler. So despite being the largest engine ever built, GE officially stated that per pound of thrust, the G9X is the quietest engine they have ever produced. Now, moving that much air requires a very special type of a fan. If you look closely at the front of the G9X, you'll notice it only has 16 fan blades. You would think a bigger engine needs more blades, but aerodynamics is a funny thing. Fewer blades mean less weight and less aerodynamic drag. But to make 16 blades do the work of 22, they have to be incredibly wide and perfectly shaped. These blades are made of 4th generation carbon fiber composites. They are incredibly stiff, but pure carbon fiber has a problem. It can be brittle. If a large bird strikes a purely carbon fiber blade at 500 miles an hour, it could shatter. So GE engineers added steel leading edges to slide through the air and deflect impacts. And they used fiberglass for the trailing edges to give the blade just enough flexibility to absorb a shock without snapping. But getting this massive fan off the ground presented a massive headache before the engine ever even made it to a Boeing aircraft. Whenever a company builds a new engine, they have to fly it on a testbed plane first. General Electric usually uses a heavily modified Boeing 747. But when they wheeled the G9X out to their 747-100 test plane, they realized the engine was so ridiculously big that it would literally scrapple the runway. They had to upgrade their test bed to a Boeing 747-400, which sits slightly higher. Even then, Boeing had to engineer a completely custom pylon to attach it to the wing, and they had to tilt the entire G9X upward by 5 degrees compared to the other 3 engines on the plane, just to give it enough ground clearance during takeoff and landing. Imagine looking out the window of a 747 and seeing one engine that is twice the size of the others, tilted slightly toward the sky. That is what it took just to test this thing. Once the air gets past the giant fan, we enter the core, and this is why the G9X sounds like the pure science fiction. To get the maximum amount of energy out of a drop of jet fuel, you have to squeeze the air as tightly as possible before you ignite it. The G9X has an overall pressure ratio of 60:1. The air entering the combustion chamber is compressed to 60 times the pressure of the outside atmosphere. It is violently squeezed through an 11-stage high-pressure compressor. By the time fuel is injected, the air is practically a solid wall of energy. But when you squeeze air that tight and burn it that efficiently, you generate an ungodly amount of heat. The inside of the G9X reaches temperatures of 2400 degrees of Fahrenheit. That is roughly 1315 degrees Celsius. Normally, engineers solve this by bleeding off some of the cool air from the compressor and channeling it through tiny holes in the turbine blades to keep them from melting. But bleeding off air means you lose efficiency. So GE completely changed the materials. They heavily utilized ceramic matrix composites, or CMCs, in the hottest part of the engine. CMCs are made of silicon carbide ceramic fibers embedded in a ceramic resin. They are 1/3 the weight of metal, twice as strong, and most importantly, they can brush off 2400 degree heat without breaking a sweat. Because they can handle the heat natively, the engine needs 20% less cooling air. That air stays in the main flow path, generating more thrust and burning less fuel. And it's not just ceramics. The G9X represents a massive shift in how engines are physically manufactured. It features over 250 parts that are additively manufactured. That's a fancy way of saying 3D printed. But we aren't talking about desktop plastic printers. We are talking about electron beam melting, where a high-powered beam fuses layers of titanium aluminate powder micron by micron. The low-pressure turbine blades are 3D printed. The fuel nozzles are 3D printed. By printing these parts, engineers can design complex internal cooling channels that are physically impossible to cast or forge using traditional metalworking. And because they are printed as a single piece, there are fewer welds, fewer joints and less weight. But none of this high-tech wizardry matters if the engine breaks down in the real world. And the real world is incredibly harsh. A huge portion of the orders for the Boeing 777X are coming from Middle Eastern airlines like Emirates and Qatar Airways. These planes are going to be spending thousands of hours flying over expansive deserts, sucking in fine sand and dust. If sand gets into a 2400-degree engine core, it melts into glass, clogs the cooling holes and destroys the engine. GE couldn't just wait and see what would happen, so they went to extreme lengths. They literally hired PhD-level geologists to analyze the exact chemical makeup and consistency of the airborne dust found at cruising altitudes over the Middle East. It's incredibly fine, almost like talcum powder. Back at their testing facility in Ohio, they built a bespoke rig that blasted this custom engineering dirt directly into the core of a running GE9X for thousands of simulated flight cycles. They intentionally tried to choke their own masterpiece to death, just to prove that the 3D printed nozzles and the CMC components could survive the harshest environments on the Earth. When you put all of this together, the 134-inch fan, the 10:1 bypass ratio, the 60:1 pressure ratio, the 3D printed titanium, and the ceramic composites, you get an engine that is a full 10% more fuel efficient than the G90, while producing 50% fewer NOx emissions than current regulations require. The G9X isn't just a bigger engine, it is a fundamental shift in how we move massive amount of weight through the air. As the Boeing 777X finally gears up to enter commercial service, it is going to be riding on the back of an engineering marvel that redefines what is possible in modern aviation. If you made it this far, I really hope you enjoyed this deep dive into the mechanics of the G9X. Let me know down in the comments what part of this engine blows your mind the most. Is it the 3D printing, the size of the fan, or that crazy pixie dust test? And of course, if you haven't already, please drop a like on the video and subscribe to the channel, so you don't miss our next deep dive into the machines that connect our world. Thanks for hanging out, and I'll see you in the next one. Ever wondered why airlines basically turned their backs on the Airbus A380, yet they are still lining up for the Boeing 777X, even though it is nearly 7 years late? Now, I'm not talking about the usual "it's too big" argument. I'm talking about the hidden specs. For instance, did you know the A380 would be 15% more fuel efficient today if Airbus hadn't gambled on versions that were never ever built? There is a lot of engineering drama behind these two jets that rarely makes the headlines. You will want to see this. And hey, if you find this breakdown interesting, hit the subscribe button. It really helps a small creator like me to keep digging into these stories. Let's get into it. Infrastructure integration and geometric constraints. Firstly, let's start with those fancy wingtips on the 777 and look at what they really give to the airlines. The most significant operational hurdle for ultra-large aircraft is their interaction with existing airport geometry. The Airbus A380 was famously designed to fit within an 80-meter by 80-meter box, a constraint that dictated every major aerodynamic decision. The A380-800 is a permanent ICAO Code F Group 6 aircraft. This designation requires airports to provide runways with a minimum width of 60 meters and taxiways with a minimum width of 23 meters, along with significantly increased separation between parallel taxiways and runways to prevent wingtip collisions. The global adoption of the A380 necessitated billions of dollars in infrastructure upgrades, from strengthening bridges to installing specialized dual-level jet bridges. These costs acted as a massive entry barrier, effectively limiting the A380 to approximately 60 to 80 major global hubs. The Boeing 777-9 approaches this problem with a geometric dual identity. During flight, the wingtips are extended to a span of 71.8 meters, placing it in the same Code F category as the A380 for airside operations such as takeoff and landing. So what I mean, the 777X also require runways with a minimum width of 60 meters. However, upon exiting the runway, the outer 3.5 meters of each wing fold vertically, reducing the wingspan to 64.8 meters. This allows the 777-9 to operate as a Code E Group 5 aircraft on the ground, even loops as the Boeing 777-300ER and Airbus A350-1000. The 777-9 is notably longer than the A380, making it the longest passenger airliner ever produced. This length presents its own challenges for gate depths, but the folding wingtips eliminate the need for the lateral space expansions that the A380 demanded. Maneuverability and ground operations. The hidden complexity of ground maneuvering lies in the minimum turning radius and the 180-degree turn capability. The A380, despite its mass, achieves a surprisingly tight turn width of 50.91 meters, but only though the use of differential braking and asymmetric thrust, techniques that increase the tire wear and engine stress. The 777-9 requires a wider 59-meter pavement width for a standard U-turn without differential braking. A critical deal breaker for the A380 in ground operations is its turnaround time. Due to its double-deck configuration, the A380 requires specialized catering trucks and cleaning crews that can access both levels simultaneously. A typical long-haul turnaround of an A380 takes approximately 180 to 210 minutes, whereas the 777-9 is targeted to achieve turnarounds in 90 to 120 minutes, significantly improving aircraft utilization rates. Aerodynamic architecture and wing physics. The divergent philosophies of Airbus and Boeing are most apparent in the wing design. The A380 wing was over-engineered for a larger Dash 900 stretched variant that was never built, resulting in a wing area that is excessively large for the current Dash 800 model. Aspect ratio and induced drag penalties. The aspect ratio, AR, of a wing is defined as the square of the wingspan, B, divided by the wing area, S. For the A380, the AR is approximately 7.5 to 7.8, which is significantly lower than the 9.0 to 9.5 found on the newer twin jets like the 787 and A350. This low aspect ratio is a direct consequence of the 80-meter wingspan limit. To provide enough lift for a 575-ton aircraft within that span, engineers had to increase the wing height, leading to a massive wing area of 845 meters squared. The aerodynamic penalty is severe. Induced drag due to weight, accounts for a 50% of total drag at cruise, which is 10% higher than it would be with an optimal 90-meter wingspan. The 777-9, by utilizing carbon fiber reinforced polymers CFRP and folding wingtips, achieves an aspect ratio of approximately 11.04. This slender wing generates lift much more efficiently and allowing for a higher cruise speed of Mach 85 compared to the A380's economical Mach 83. Wing loading and thrust-to-weight ratios. Wing loading, W divided by S, is a critical metric for takeoff performance and cruise efficiency. The A380 has a relatively low wing loading at MTOW due to its oversized wing, while the 777-9 operates at much higher pressures. The higher thrust-to-weight ratio of the 777-9, powered by the massive G9X engines, allows for superior climb gradients and better performance in hot and high conditions. The A380, while powerful, is hampered by its massive empty weight, which is nearly 10,000 kilograms heavier than the 777-9. Propulsion systems: G9X versus the quad-engine paradigm. The propulsion system is perhaps the single most important deal-breaker in the comparison. The A380 utilizes 4 engines, from either the Engine Alliance GP7200 or Rolls-Royce Trent 900. These engines represent late 1990s technology, which was quickly eclipsed by the G9X and Trent XWB generations. Thermodynamic efficiency and the GE9X. The G9X is the largest and most powerful commercial engine ever built, featuring a 134-inch fan and 27:1 compressor pressure ratio. It offers a 10% reduction in specific fuel consumption, SFC, compared to the G90-115B, and a nearly 20–25% improvement over the engines powering the A380. One hidden specification is the engine weight fraction. On the 777-9, the 2 G9X engines represent a smaller percentage of the MTOW than the 4 engines on the A380, despite the G9X's massive size. This is because the twin-engine configuration eliminates the need for 2 extra pylons, dual fuel lines, and complex quad-engine synchronization systems, engine maintenance cycles, and durability issues. A significant deal-breaker for the A380 is the sheer cost of engine maintenance. With 4 engines, an airline faces twice as many shop visits as a twin-engine operator. Engine maintenance for an A380 can reach $30,000 per flight hour, whereas a 777 operator typically spends $7,000 to $9,000 per hour on a 300ER, with the 777-9 expected to be slightly higher due to the complexity of the G9X. However, the G9X has faced its own challenges. In early 2026, a durability issue was identified regarding a seal in the high-pressure compressor. This issue led to a temporary flight test slowdown, with only 2 of 5 test aircraft flying in February 2026. While Boeing maintains this will not delay the first delivery in 2027, the long-term reliability of these ultra-high-pressure engines remains a concern for launch customers like Emirates and Lufthansa. Powerment dynamics, ACN, ACR, and CDF analysis. A hidden specification critical to airport planning is the impact of the aircraft's weight on the physical life of the runway. This is measured through the Aircraft Classification Number, ACN, or the Newer Aircraft Classification Rating, ACR. The powerment-friendly giant. Despite its 575-ton mass, the A380 is famously powerment-friendly. This is due to its 22-wheel landing gear configuration, which distributes the weight more broadly than the 14 wheels on the 777-9. The A380's main landing gear, MLG, consists of 2 6-wheel body gears and 2 4-wheel wing gears. The cumulative damage factor, CDF, analysis shows that the A380's wide gear track, 12.5 meters between wing gear axles, places the heaviest loads on the sections of the runway that are rarely used by other wide-body aircraft. Standard long-range jets, like the 777-300ER, have tracks between 10.6 and 11.9 meters. Consequently, The A380 contributes roughly 30% less to the peak powerment damage of a typical fleet mix than its gross weight would suggest. 777-9 powerment stress and ACR values. The Boeing 777-9, by constant, concentrates its 352-ton taxi weight onto two six-wheel trucks. To support this weight, the 777-9 uses higher tire pressures, 229 psi, than the A380, 218 psi. Higher tire pressure leads to higher vertical strain in the upper layers of the asphalt, potentially accelerating powerment cracking. The deal breaker here for small airports is that while the 777-9 fits in the gate, it may require runway strengthening if the subgrade is ultra-low, category D, as its ACR exceeds the PCN of many secondary airports. Cabin environment and psychoacoustics. Passenger experience is often marketed through luxury, but the true differentiators are noise levels, cabin altitude, and humidity, factors that directly influence jet lag and fatigue. The A380 noise advantage. The A380 remains the quietest large aircraft ever built. Measurements show that at cruise, the A380 mid-cabin noise level is approximately 68 dB, compared to 73 dB of the 777-300ER and roughly 70 to 71 dB for the 787 and A350. Because the decibel scale is logarithmic, a 5 dB difference represents a nearly 300% difference in sound intensity and 25 to 30% difference in perceived loudness. The A380's noise profile is also flatter, lacking the high-frequency hiss of airflow found in twin jets. This makes it the perfect aircraft for ultra-long-haul premium travelers. 777X atmospheric improvements. The 777X counters the A380's quietness with superior cabin atmosphere. By utilizing the 787's environmental control systems, the 777-9 maintains a cabin altitude of 6,000 feet, even at a flight level of 41,000 feet. The A380, designed with older aluminum alloys, typically maintains a cabin altitude of 7,000 to 8,000 feet. The 777X also features higher humidity levels and advanced filtration, which reduces the dry eye and dehydration symptoms common on the A380. Economic deal breakers. The cargo revenue gap. The most profound hidden specification that led to A380's commercial failure is the cargo-to-passenger ratio. Airlines generate a significant portion of their profit from belly cargo, which subsidizes the cost of the passenger flight. The A380 is a volume-limited aircraft. Its double-deck configuration uses up almost all the internal fuselage volume for passengers, leaving very little space for freight. The A380 provides approximately 133 cubic meters of cargo space, while the 777-9 provides a massive 230 cubic meters. On a route like Dubai to New York, JFK, an A380 burns roughly 65 tons more fuel than the 777 to carry potentially only 100 extra passengers. This makes the A380 economically unviable on any route where it cannot maintain a passenger load factor of at least 85%. The 777-9, with its high cargo capacity, can remain profitable even with a 60% passenger load, because the belly freight covers the fuel bill. The A380neo, engineering realities and failure. The A380neo new engine option was a proposed upgrade meant to bridge the efficiency gap between the A380 and the 777X. However, the project was never launched due to a series of technical and financial death spirals. To achieve a 10 to 15% fuel burn reduction, the A380 requires modern engines like the Rolls-Royce Trent XWB or a D-rated GE9X. These engines have significantly larger fan diameters, 118 to 134 inches, than the original Trent 900, 116 inches. The heavier engines would increase the bending moment of the wing, requiring hundreds of kilograms of structural reinforcement. To maintain ground clearance for the larger nacelles, the landing gear would need to be lengthened, adding even more weight. Larger nacelles increase the wetted area and form drag, which would negate about 2 to 3% of the engine's efficiency gains. Airbus calculated that the OEW, operating empty weight, increase would be so significant that the NEO would only offer a 5 to 10% net improvement in fuel burn, not enough to justify the $3 billion development cost. Engine manufacturers like Rolls-Royce were unwilling to invest in a backspoke engine for the A380 when the total remaining order book was so small. Unlike the A320neo, which had thousands of orders, the A380 was a one-customer aircraft, Emirates. Developing an engine for a fleet of only 100, maybe 200 aircraft was commercially impossible for the OEMs, especially when they could focus on the A350 and 787 markets, where thousands of engines would be sold. System architectures and hidden specs. Beyond the airframe and engines, the internal systems of this aircraft represent two different eras of electrical and hydraulics engineering. Hydraulic pressure 5000 psi versus 3000 psi. The A380 was the first commercial aircraft to utilize a 5000 psi, 35 megapascal hydraulic system, a significant jump for the industry standard 3000 psi. High-pressure hydraulics allowed Airbus to use smaller, lighter actuators and thinner titanium piping to move the massive flight control surfaces. This saved approximately 1000 kg in weight. The 777X maintains a hybrid approach, but relies more on electromechanical actuators for secondary systems, reducing the reliance on heavy hydraulic fluid lines throughout the cabin. Electrical generation. Variable frequency versus constant speed. The A380 utilizes 450 kilowatt variable frequency generators. By allowing the generator frequency to vary with engine RPM, Airbus eliminated the heavy and maintenance-intensive constant speed drive (CSD) found on older jets. The 777X takes this further, utilizing a 787-style, more electric architecture, where the auxiliary power unit (APU) and main engines provide massive electrical reserves to power the environmental control systems (ECS) without the need for traditional bleed air from the engines. This no-bleed or low-bleed approach improves engine efficiency by 2–3% by not siphoning off high-pressure air from the cabin. Operational resilience, fact check and 2026 outlook. As of February 2026, the status of both programs has been affected by the global recovery and technical setbacks. The 777X program is currently 6 years behind its original schedule, with the first delivery to Lufthansa now expected in second quarter of 2027. The FAA and EASA have increased their oversight, requiring a phased type inspection authorization that has slowed progress. Despite this, the order book has remained resilient, with Emirates adding 65 more 777X units at the Dubai Air Show 2025, bringing their total commitment to 270 aircraft. The A380 has defined early retirement predictions. As of April 2024, there were 189 aircraft in service with 10 operators. By 2026, the global fleet valuation has actually increased by 2.8%, as airlines realize they cannot meet post-pandemic demand without the super jumbo's capacity. Emirates plans to fly the A380 until 2040, investing in massive cabin refurbishments to keep the fleet modern while waiting for the 777X. Maintenance and life cycle costs. Maintenance costs are the ultimate hidden spec that determines the long-term viability of an airframe. The deal breaker for many A380 operators like Air France and Thai Airways was the sunk cost of point-to-point operations. By the time an A380 is turned around and ready to fly, the airline has already spent nearly $500,000 in fuel, staff, and landing fees. On a twin jet, these fixed costs are significantly lower, providing the airline with more exit liquidity if a route underperforms. Now share your thoughts in the comments. Maybe you know more interesting hidden specs. I'll be really interested to hear your opinion. Don't forget to like and subscribe. But now let's meet in some of these videos. See you! Look at this airplane. This is the Embraer E2, also known as the Profit Hunter. With its tech shark livery, it looks like the future of aviation. It is the quietest and the most fuel-efficient narrow-body aircraft in the sky. And for us, the passengers, it is a dream. Why? Because there are no middle seats. It's a 2+2 configuration. No more fighting for an armrest with a stranger. On paper, this plane is a masterpiece of Brazilian engineering. It was supposed to be the giant killer, the plane that would make Boeing and Airbus nervous. It consumes 17% less fuel than the previous generation and has the most advanced fly-by-wire system in its class. But here is the mystery. Airlines are not buying it. While Airbus is celebrating hundreds of orders for its rival, the A220, the Embraer E2 is struggling to find a home. In the world of aviation, being the best doesn't always mean you win. Sometimes you can build the perfect machine, but the market simply refuses to take it. How can a plane that is so right be so wrong? Today we are going deep into the numbers. We are looking at why this tech shark is becoming a headache for investors instead of a goldmine. It's a story of great engines, bad timing, and very expensive legal trap. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. The engine course. Innovation versus reliability. To understand why the E2 is struggling, we have to look under the wings. This is the Pratt & Whitney GFT, the geared turbofan. It is a technical miracle, but for many airlines it has become a nightmare. Here is the simple science. In a normal jet engine, the fan and the turbine spin at the same speed. But in the GFT, there is a gearbox. This allows the big fan at the front to spin slower, while the turbine inside spins much faster. This makes the engine incredibly quiet and saves nearly 20% on fuel. For an airline, that sounds like a license to print money. But here is the catch. This technology is extremely complex. The gearbox and the new materials inside the engines are under massive heat and pressure. In the first years of operation, These engines started showing teething problems. We are talking about hardware failures, cooling issues, and parts that wear out much faster than expected. Normally, you fix a part and the plane flies again. But today, the global supply chain is broken. There aren't enough spare parts. Now let's look at the math. In the first year of a new aircraft's life, you expect it to be in the air 10 or 12 hours a day. But many E2 operators found their planes stuck on the ground for months waiting for engine repairs. If we compare the E2 to the older E1 during their first years, the dispatch reliability, which is how often the plane is ready to fly on time, was significantly lower for the new model. Airlines hate uncertainty. When a CEO looks at the E2, they don't just see a fuel-efficient jet, they see a risk. They ask, will this plane fly tomorrow or will it sit in a hangar because of a broken gear? For many, the 20% fuel saving isn't worth a plane that cannot fly. The legal trap. How unions grounded a giant. But wait, if the engine is the only problem, Embraer could just fix it, right? Wrong. The biggest problem for the E2 is not mechanical. It is a legal trap called scope clauses. To understand this, we have to look at the United States, the biggest market for regional jets in the world. In the US, major airlines like United, Delta, and American don't fly their own small planes. Instead, they hire regional airlines to do it for them. But here is a very strict contrast between the big airlines and their pilot unions. This contrast is the scope clause. It says, you can use regional pilots, but only if the plane stays under a certain size and weight. There is one specific number that killed the E2 – 76,000 pounds. That is the maximum takeoff weight, MTOW, allowed for regional jets in America. The older Embraer E175 fits this rule perfectly. It is the king of the US skies because it weighs exactly what the union allows. But the new E175 E2, because of those big heavy fuel-efficient engines and those advanced wings, it weighs nearly 89,000 pounds. It sounds crazy, doesn't it? Embraer built a plane that is better, cleaner and more quiet. But because of a piece of paper signed by lawyers and unions, it is too heavy to fly in the US. The unions refuse to change the weight limit. They want to protect the jobs of pilots who fly the bigger mainline jets. They fear that if they allow heavier regional planes, the big airlines will stop using large jets and replace them with smaller ones. Embraer made a massive gamble. They believed the rules would change by the time the E2 was ready. They were wrong. The rules stayed the same. And now the E175 E2, the most important version of the plane, has 0 customers in the world's most profitable market. It is a tragedy of modern aviation. You can spend billions of dollars on engineering and create a masterpiece, but you can still be defeated by a single line of text in a legal contract. The shadow of Airbus, a David versus Goliath battle. Now imagine you are a CEO of a mid-sized airline. You need a new jet. You look at the Embraer E2, but then you look at its biggest rival, the Airbus A220. And this is where the shadow of the giant falls over Embraer. The A220 was not always an Airbus. It started as the Bombardier C Series, a brilliant plane from Canada. But Bombardier almost went bankrupt building it. Airbus stepped in and used its massive global power to turn it into a superstar. How does Airbus win? It's simple. They are a one-stop shop. Airbus has deep pockets and a huge family of aircraft. When they talk to an airline like JetBlue or Delta, they don't just sell one plane. They can say, if you buy 50 of our big A321s, we will give you a massive discount on 20 small A220s. Embraer cannot do this. They are a smaller independent company. They have to make a profit on every single jet they sell. They cannot play the same money game as the giant like Airbus. The numbers tell a painful story. Airbus has over 800 orders for the A220. Embraer? They have around 200 for the E2. In the business world, success creates more success. Airlines see everyone else buying the A220, so they feel it is a safer investment. But there is one more secret weapon Airbus has – the pilots. If an airline already flies the Airbus A320, the most popular plane in the world, it is much easier to train their pilots to the A220. It feels like a part of the same family. If they buy the Embraer, they have to build a completely new department for training and maintenance. For many airlines, even if the Embraer is a slightly better technical machine, the Airbus is the better business decision. Embraer is fighting a war against a company that has more money, more influence, and a bigger family. It is a fight that is almost impossible to win. Global survival. Looking for a new home. So, is the E2 dead? Not exactly. Since the US market is blocked by legal rules and Europe is dominated by Airbus, Embraer is looking at the rest of the world. In places like Brazil, India, and Southeast Asia, the scope clause doesn't exist. These regions have thousands of islands and growing cities that need a plane exactly like the E2. Something bigger than a small turboprop, but smaller and cheaper to run than a massive Boeing 737. But the most important test is happening right now, in Canada, with Porter Airlines. Porter is the hero of the E2 story. They didn't just buy a few planes, they ordered up to 100 of them. They are using the E2 to fly long distances, like Toronto to Los Angeles or Florida. Porter is essentially a living laboratory. If Porter can prove that the E2 is reliable, that the engines stay healthy, and that passengers love the 2+2 seating, other airlines will stop being afraid. Porter is the advertising face that Embraer desperately needs. If Porter succeeds, the E2 survives. If Porter struggles, E2 may stay a niche aircraft forever. However, Embraer is smart. They are already preparing a plan B. They know the E2 might never be a global bestseller like the E1 was. So they are moving into a new space – sustainable aviation. While Boeing and Airbus are fighting over big jets, Embraer is designing a new generation of green planes. They are working on high-tech turboprops and even electric aircraft under their Energia project. Their strategy is simple. If you can't beat the giants in the jet market, lead the way in the green market. Embraer isn't giving up. They are looking for every gap in the market that the giants have missed. They are betting that the future of flying isn't just about being big. It's about being smart, efficient, and ready to pivot when the world changes. Now I want to ask you, would you prefer the Embraer E2 over Boeing or Airbus? And what do you think about this company in general? I'd be interested to hear your opinion. If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you next time. Have you ever lost your house keys? It happens to everyone. Now imagine losing something much bigger. Imagine the world losing 4 massive Boeing 777 airplanes. Each one weighs 200 tons. In December 2022, something incredible happened. Several of these jets, which used to fly for Singapore Airlines, took off from storage airports in Uzbekistan and Cambodia. They climbed into the sky and then they simply dissolved into thin air. But they didn't crash. There was no emergency. Instead, these American-made giants secretly landed in Tehran. How is this possible? How did Mahan Air, the most sanctioned airline in the world, manage to smuggle 4 modern airliners right under the nose of the CIA? Let's find out. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. Chapter 1. The Madagascar Gambit. So, how do you legally buy a plane if the world forbids you from buying one? The answer is simple. You don't use your own name. You use a shell company. This is a fake business set up in places like UAE or Gambia. On paper, it looks like a normal company buying a plane for travel. But in reality, it is just a mask. But buying the plane is only step one. You also need to register it. For these Boeings, the smugglers used a clever trick. They registered the planes with the code 5R, which belongs to Madagascar. Why Madagascar? Because the aviation control there is weak, and regulations are easy to bypass. They created a fake airline that claimed it would fly charter flights for tourists. It was the perfect cover. Then came the escape. The planes flight a normal flight plan, for example flying towards Uzbekistan. They took off and everything looked standard. But then, they reached a specific point in the sky, usually over Afghanistan. At this exact moment, the pilot turned off the transponder, the device that tracks the plane. The dot disappeared from the radar screens. The plane became a ghost. The pilot changed course and flew directly into Iran. This is known as the blue service method. It is the exact same trick they used to smuggle Airbus A340s before. It is risky, but it works. Chapter 2. The Technical Detectives. Why did they choose these specific planes? Why is the Boeing 777-200ER? These were not new jets. They were retired planes from Singapore Airlines and Knox Scoot. For a long time, they were just sitting in the desert, like the famous airplane graveyard in Alice Springs, gathering dust and waiting to be scrapped. Then, they were moved to Asia. But the real secret lies under the wings, the engines. These planes are powered by the Rolls-Royce Trent 800. This is the critical detail. Most modern Boeing 777s use G90 engines made by General Electric. The problem for Iran is that General Electric is an American company that watches everything. They track every screw and every sensor. It is a nightmare for smugglers to get parts for them. Rolls-Royce is British. While they are also under sanctions, the black market for their parts is slightly softer. Iran may already have old connections to get what they need. There is also a simple economic reason. Nobody else wants these planes. The Trent 800 is an older, thirsty engine. It burns a lot of fuel compared to modern jets. On the legal market, these planes are almost worthless. This makes them incredibly cheap to buy with cash. For a smuggler, they were the perfect bargain. Chapter 3. Cannibalism and donor planes. You might wonder, why did they steal 4 or 5 planes? Maintaining just one huge Boeing is already a headache under sanctions. Maintaining a whole fleet seems impossible. The strategy is dark but smart. In the aviation world, it's called cannibalism. Here's how it works. Iran buys 4 planes, but they only plan to fly 2 of them. The other 2? They are doomed. They become organ donors. When a fuel pump breaks or a computer fails on the flying plane, they don't order a new part from America. They just walk to the hangar, rip the part out of the grounded plane, and install it on the active one. It is much cheaper and more reliable than trying to find smuggled spare parts on the black market every week. But hardware is only half the battle. These planes have no access to official Boeing software updates. There are no service manuals or technical support. If a warning light turns on, you can't call customer service. This has forced Iranian technicians to adapt. Over the years, they have become masters of reverse engineering. They have learned to fix complex American technology without instructions, keeping these metal birds in the sky long after they shouldn't have been grounded. Chapter 4. Geopolitics and the powerlessness of the West. This brings up to the big question: where was the United States? The US had the most powerful military and intelligence network in the world. Why didn't they shoot these planes down or arrest the pilots? The answer is a frustrating legal dialogue. You cannot simply arrest a plane while it is flying 30,000 feet in the air, especially over neutral or friendly territory. Until the wheels touch the ground in a country that follows US laws, American authorities are powerless. They likely watched the shaft happen on their screens, but they couldn't do nothing to stop it. So what is the future of the stolen giants? They cannot fly to London, Paris or Berlin. If one of these stolen 777s lands in Europe or North America, it will be seized immediately by lawyers and authorities. Instead, these planes will fly a limited network.
You will see them on domestic routes inside Iran or flying to friendly hubs like Moscow, Beijing, Istanbul and maybe Dubai. They are big birds in a small cage. There is a deep irony here. These are American machines, built by American workers in Seattle. Now they are the pride of a regime that considers the US as an enemy. It is a strange reality. A country that burns American flags on the streets is desperate to fly in American planes in the sky. Conclusion: the price of risk. So Iran did it. They showed the world a masterclass of bypassing sanctions. They tricked the regulators and they got their prize. But this is a victory with a very heavy price. Ask yourself this honestly. Would you feel safe on that seat? We are talking about a plane that is being kept alive by cannibalizing other aircraft. It has not had an official technical inspection for years. It is flying without manufacturer's safety net. It is basically a Frankenstein monster of the skies. Ultimately, this story is not just about aviation enthusiasts or secret agents. It is a story about survival. It shows us exactly how far a government will go to keep its economy moving. Every rule in the book. Now I want to turn the question to you. Knowing the history of these ghost planes, knowing they are fixed with scavenged parts, would you buy a ticket? Write in the comments below. Would you risk flying on this Mahan Air 777? If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you next time.
Picture this. In the early 2000s, Airbus officially launched the A380, a massive double-decker engineering marvel. Over the next few years, international airlines are throwing billions of dollars at it. Emirates, Singapore, British Airways, Qantas, they are all lining up. But the US carriers? They didn't order a single one. Not one. It is honestly one of the most fascinating anomalies in commercial aviation history. You have the country with the most robust aviation market on the planet, with incredible global reach, and they just completely blanked the super jumbo. Why? Today we are breaking down the real reasons, and I promise you, it goes way deeper than just the plane was too big. It's a story of brutal airline economics, incredibly bad timing, and a hidden cargo war. But before we unpack the real reason US carriers dodged the A380, do me a huge favor, hit that like button and subscribe to the channel. It takes 2 seconds and it really helps push these aviation deep dives out to more people. Alright, let's get into it. To really understand this, we have to start with a massive philosophical disagreement between Airbus and Boeing about the future of travel. When Airbus designed the A380, they were looking at a map of the world and seeing the massive congestion. Their bet was that mega hub places like London, Heathrow, JFK, Tokyo, Dubai were going to run out of runway slots. So the only way to move more people was to build a much bigger plane. You fly 500 to 600 people between these massive hubs on an A380 and then distribute them on smaller planes to their final destinations. But US carriers saw the completely opposite future. They were looking at a point-to-point model. The US airlines realized something incredibly important about their most profitable customers – business travelers. Corporate travelers don't care about double-decker plane with a bar. They care about their schedule. If you are flying from New York to London on business, you want the option to leave at 8 am, noon, 4 pm, 8 pm or 10 pm. You want frequency. You can't do that with an A380. If an airline uses an A380, they have to consolidate all those passengers into 1 or 2 massive flights a day to actually fill the plane and make it profitable. US airlines knew that if they dropped their flight frequencies to fill an A380, those high-paying business travelers would simply book a ticket on a competitor who offered a flight time that better fit their schedule. At the exact same time the A380 was coming to life, Boeing was developing the 787 Dreamliner. It was a smaller, highly efficient twin-engine jet that could fly incredibly long distances, completely bypassing those mega hubs. The US airlines basically looked at the A380 and realized it solved a problem they weren't planning on having. But let's say US carriers actually wanted the A380. Let's say United or Delta looked at it and thought, maybe we can make this work on a few ultra-dense routes. Well, there was a massive elephant in the room. The timing of the A380 was absolutely catastrophic for the American aviation industry. The A380 program was launched in late 2000. It first flew in 2005, and it entered commercial service in 2007. Look at what was happening to the legacy US carriers during that exact time window. In 2001, the aviation industry suffered an unprecedented shock. Between 2002 and 2005, United Airlines, US Airways, Delta Airlines, and Northwest Airlines all filed for Chapter 11 bankruptcy protection. Then the 2008 global financial crisis hit, and by 2011, American Airlines was also in bankruptcy. During the critical years when Airbus was desperately trying to lock in launch customers and fill its order book, every major legacy US airline was literally fighting for its life. They were slashing pensions, cutting routes, and trying to survive. They had zero capital to risk on a totally unproven $400 million four-engine experimental aircraft. By the time the US carriers finally merged, restructured, and returned to profitability in the 2010s, the era of the four-engine jet was already over. The twin-engine revolution had won. And speaking of twin-engine jets, we have to talk about the secret moneymaker of international flights, belly freight. When you fly internationally, your passenger ticket is only part of airline's revenue. The cargo hold underneath your fleet is packed with commercial freight, and that freight is highly lucrative. Sometimes the cargo alone covers the operating cost of the flight, and the passenger tickets are just pure profit. This is why the A380 got completely decimated by its main competitor, the Boeing 777-300ER. Because the A380 has a second passenger deck, the structural floor of the main deck is lower. This severely limits the volume of the cargo hold relative to the massive size of the aircraft. To put some real numbers on this, a Boeing 777-300ER has a total cargo volume of roughly 7,120 cubic feet. The Airbus A380, despite being a tremendously larger airplane, has a cargo volume of only about 6,190 cubic feet. US carriers rely heavily on cargo revenue. If American or United swapped a 777 for an A380 on a major international route, they were suddenly taking a massive hit on their cargo capacity. They would be burning more fuel with four engines while carrying less profitable freight. The math just didn't work. Now here is a piece of the puzzle that almost everyone missed. It's a massive loophole in international aviation. US airlines didn't actually need to buy the A380 because their European partners bought it for them. Let me explain. Modern international aviation is heavily dictated by what are called joint ventures. These are legally immune partnerships where airlines essentially act as a single company on specific international routes. American Airlines has a massive transatlantic joint venture with British Airways. Delta Airlines has one with Air France. Both British Airways and Air France bought and operated the A380. So if American Airlines customer wanted to fly from Miami to London on an A380, American would just sell them a code-share ticket on a British Airways A380. American Airlines still got a piece of the profit from that flight, but they completely avoided the risk. They didn't have to spend $500 million buying the plane. They didn't have to train dedicated pilots for it. They didn't have to maintain 4 massive Rolls-Royce engines. They got the A380 revenue with zero A380 liability. It was a financial cheat code. because integrating an A380 into a US fleet would have been an infrastructure nightmare. The FAA classifies the A380 as a Design Group 6 aircraft. It has a wingspan of nearly 262 feet. It is incredibly heavy. To handle this plane, airports have to physically change. Taxiways have to be widened, so the massive outboard engines don't hang over the grass and stack up dirt and debris. Runways need reinforcing. You can't board 500 people through a single door. It takes way too long. And an airplane sitting at a gate isn't making money. You need specialized multi-level dual jet bridges to board the upper and lower decks at the same time. During the 2000s, US airlines were not about to go to airport authorities in places like Chicago, Newark or Dallas and say, "Hey, we need you to spend hundreds of millions of dollars upgrading the terminals just so we can fly this one specific type of airplane." It just wasn't going to happen. There's also the brutal reality of aircraft asset management. Airlines aren't just in the business of flying planes. They are in the business of buying and selling them. When a US legacy carrier buys a jet, they already have a spreadsheet projecting what they can sell it for in 15 or 20 years on the secondary market. If you buy a 777 or a 787, you know that in 15 years there will be dozens of cargo companies, charter operators or smaller foreign airlines begging to buy it from you. But who do you sell a used A380 to? Because it requires such specific routes and massive airport infrastructure, the secondary market for the A380 was basically non-existent. We literally saw this play out. A few years ago, the very first A380s delivered to Singapore Airlines hit their 10-year lease mark. They were returned to the leasing company, and because no other airline in the world wanted them, this massive, decade-old flagship aircraft were immediately chopped up for scrap. For an airline accountant at Delta or United, seeing a 10-year-old aircraft get scrapped is a nightmare scenario. The residual value risk was just entirely too high. Finally, you have to look at the cabins. To make the fuel burn of those four engines profitable, the A380 relies heavily on ultra-premium first class. Airlines like Emirates and Singapore put in enclosed suites, showers and onboard lounges. They charge $10, $15, sometimes $20,000 for those tickets. That revenue offsets the operating costs. But the US airlines have a totally different domestic corporate culture. In the wake of financial crisis, American corporations changed their travel policies. Almost no company was approving international first-class expenses anymore. Because of this, US airlines were actually in the process of ripping international first class out of their planes entirely, replacing it with highly efficient, dense business class cabins. If a US airline tried to fly on an A380 filled mostly with economy passengers and standard business class, without those $15,000 first class suites to subsidize the flight, they would bleed money on every single sector. When you put all these pieces together, the demand for high-frequency scheduling, the bankruptcies on early 2000s, the lack of belly cargo space, the joint venture loopholes, the infrastructure costs, and the non-existing secondary market, it becomes completely obvious why US carriers never touched the A380. It wasn't a mistake or an oversight, it was a highly calculated financial rejection. The US market was playing a completely different game than the one Airbus designed the A380 for. Aviation is a brutal business, and sometimes the most incredible engineering achievements simply don't survive the spreadsheet. If you found this discussion interesting and you made this far into the video, you definitely need to be subscribed. Drop a like on the video and let me know down in the comments what you think. Did Airbus make a massive miscalculation with the A380, or was it just the right plane at the absolute worst time?